properties of ceramics. Ceramics are composed of at least two elements, and consequently their structures are in general more complicated than those of metals. While most metals are face-centered cubic (FCC), body-centered cubic (BCC), or hexagonal closed-packed (HCP), ceramics exhibit a much wider variety of structures. Generally, they are inorganic and nonmetallic. Development of ceramics helps to decrease the demand in industries. Ceramics usually withstands high temperature, but it has a poor mechanical properties. These properties of ceramics, however, also depend on their microstructure. Ceramics are by definition natural or synthetic, inorganic, nonmetallic, polycrystalline materials. Advanced ceramics are fine particles in nature. They possess microscopic grain boundaries and microstructure pores. This diffuses the light, and it is difficult to transmit the light. Single crystals have no grain boundaries or pores, hence light can easily pass through. Light can also pass through in fine ceramics if we minimize the pores and grain boundary. In addition, fine ceramics have ferromagnetic and semiconductive properties. Because of these properties, there is a change in phosphorescence due to its interactions with light and electric field. So, optical ceramics revolves around in physics that involves between the interaction between light and materials. So the key five factors is considered by the light-matter interaction and how light behaves. It also includes three main groups of optical ceramics. It is the transparent, translucent, and opaque as the material object and how to classify them. So as you can see here, this is the electromagnetic spectrum. The electromagnetic spectrum, or EM, is the range of all types of EM radiation. The visible spectrum constitutes a small window between 0.4 and 0.7 and 3.1 eV. So, alternating currents, infrared radiation, microwaves, visible light, X-rays, ultraviolet light, and etc., all produce oscillating electromagnetic fields differing only in their frequencies. And although sometimes they are thought of as being distinct, they do constitute a continuum known as the electromagnetic spectrum that spans 24 orders of magnitude of frequency or wavelengths. As you can see here in the figure, within that spectrum, the visible range occupies a small window from 0.4, 0.7, or 1.65 or 3.0. The various interactions between the electromagnetic radiation and ceramics will be discussed. However, In this phenomena that describes in this chapter relate mostly to the optical region part of the electromagnetic spectrums. So next is the basic principles. So in optical properties of ceramics, the basic principles is that when a beam of light or electromagnetic radiation impinges on a solid, as you can see here on the picture, the radiation can be transmitted through the samples and then absorbed by it and scattered at various angles. The various interactions that created by the radiation and the solids we can observe that the monochromatic ray with the frequency and the intensity can be transmitted, and it could be transmitted. But with the same frequency, the intensity is reduced and could be concluded that some is scattered, absorbed, or reflected. The scattered waves can be coherent or incoherent. Coherent is when the scattered waves constructively interfere with one another, while incoherent gives rise to other forms of scattering, like the Rayleigh scattering. So here, as you can see here, there is a formula that solves the intensity, that is the energy flux per unit area, in which the units are joules divided by m squared times s. Then dividing both sides of the equation by intensity will yield this formula. Here you can see the ITIR and IA represent the transmitted, reflected, and absorbed intensities, respectively. Then, if you divide both sides of the equation by intensity, will yield the formula where T, R, and A represent respectively the fraction of light transmitted, reflected, and absorbed.
Good day everyone, my name is Blaine P. Valencia. Today I will discuss about the key properties of ceramics. First, for a certain composition, ceramics can be transparent, translucent, or opaque. Ceramics can be made translucent by minimizing the pores and boundary elements after sintering, and by increasing crystal size in order to reduce boundary interfaces. Second, adding additives, dopants, and point defects, the colors of ceramics can be altered. If a transparent ceramic or glass is doped, for example, by the addition of transition metal ions, the material becomes colored. For example, the doping of Al2O3 with chromium 3 plus will produce ruby, which is used as an optical cavity in a solid state laser. The third property is ceramics can emit light when there is an electric field or an illumination of light of different wavelength. When a material is placed in an electric field or irradiated with light, it may itself radiate light, either electric or optical energy is absorbed and optical energy is then radiated. Materials exhibiting this phenomenon is called phosphor, and the light radiated by phosphor is what you call luminescence. Phosphors produce light as a result of excitation. Luminescence can be fluorescence or phosphorescence. The only difference between the two is the time for which emission occurs. Fluorescence occurs very quickly at less than 10 to the negative 8 seconds, while phosphorescence is slow emission over 1 second or even longer. The last of the key properties is that ceramics can reflect and or refract light. Refraction is the ability of a substance to bend light waves. It is also sometimes described as refringence. Crystals having one unique axis or optic axis along which the index of refraction is different from the index along other orthogonal axes are known as uniaxial birefringent crystals. Reflection. Reflection is when light bounces off an object. If the surface is smooth and shiny like glass, water, or polished metal, the light will reflect at the same angle as it hit the surface. Using the equation given below, which is R is equals to n2 minus n1 squared over n2 plus n1 squared, we can determine the reflectivity from the surface of various ceramics and glasses. The reflectivity is about 4% from a surface with the index of refraction of 1.5 and about 10% for a surface with an index of refraction of 1.9. A high reflectivity is often important for aesthetic reasons. The high reflectivity, R is equals to 30% of lead crystal glass contains a high amount of lead oxide, which is due to its high refractive index of 2.1. The reflectivity is more than twice that of normal silicate glasses.
Good day, everyone. I am Romel Jeremiah B. Trinidad, and today I will discuss about measurement techniques and also give some example problems. So, as we discussed earlier, the refractive index is equals to the velocity of light in vacuum and the velocity of light in medium. So here, we have the velocity of light in air, which is equivalent to 3.0 times 10 to the 8 meters per second. Then the V is the light in medium, in which our medium is diamond, is equivalent to 1.24 times 10 to the 8 meters per second. Now to solve this problem, to know the index of refraction, we must first input the formula, N equals C over V. Then we must substitute. Now we must take note that since the index of refraction is unitless, we must know that the speed of light and the speed of light in medium and in air must be similar units. So in here, we cancel this, giving us a unitless 2.419. So that is the index of refraction of diamond. Next is the Snell's law. Now, when light hits a surface or a medium, for example a diamond, the light actually slows down when it passes through. So what happens is, we have here is the incident ray. So when the incident ray reaches the in-surface, it will become a refracted ray, and the refracted ray changes direction. This means the light slowed down, and from the incident angle, we also have the refracted angle, which also changed. To clarify this, as we can see earlier, that the speed of light in air is 3.0 times 10 to the 8 meters per second, but when it reached diamond, it only became 1.24 times 10 to the 8 meters per second. This proof that when the light passes through diamond and already interacted with the interface, the light slows down and its angle changes and its direction. So here is a sample problem. Light goes from air to diamond and that the incident angle is 30 degrees. Calculate the angle of refraction, theta 2, in the diamond. So to calculate this, we have all the given that we need. First, we must input the formula of Snell's law, which is n1 sine theta equals n2 theta 2 sine theta 2. Then we segregate the units. Since we are only looking for theta 2, we must segregate n1 and n2 to the right side, leaving only sine theta 2. Then we input the values. Sine theta 2 equals 1 because the index refraction of light in air is 1. And as we solved earlier, the index refraction of diamond is 2.419. Sine 30, 30 is the incident angle, which is our theta sub 1. So sine theta 2 will be equal to 0.207. So by here, we are not yet actually done. What we are only looking for is theta 2. So we still need to divide it by sine and actually cancel the sine and move it here. So what happens after that is theta 2 equals sine to the negative 1. Sine to the negative 1 because it became 1 over sine since we divided it, and 1 over sine is equals to inverse sine. So now by solving this, inverse sine times inverse sine of 0.207 is equal to 11.9. So from an incident angle of 30 degrees, when it passes through the medium and change direction, the angle now that we have, the angle of refraction is 11.9.
Absorption and color. The color in ceramic is most dielectric and colorless. These are glasses. The electric materials have good transmission on the optical part of the spectrum. It is by adding transition metals such as titanium, chromium, iron, cobalt, nickel. Transmission ranges for optical materials. As you can see, window glass transmit light as at 1 times 10 raised to the 15 up to 7.5 times 10 raised to the 13. That is why it is used for windows. Typical semiconductor materials such as silicon and gallium arsenide are only transparent in iron range. The processes by which light is absorbed by solids are several and include The photoelectric effect, where electrons absorb incident light and are promoted into the conduction band. For this process to occur, the incident light has to be greater than the gap of the material. For ceramics, this is typically in the UV range. The split energy of transition metal ion d and f orbitals. As a result of their interaction with their local environment, this gives rise to selective absorption in the visible range. It is this absorption that is responsible for the striking colors exhibited by some glasses and gems. Reduction and radiation can give rise to color centers defined as impurity or defect into which an electron or hole is locally bound. The localization of the electron and its promotion to higher energy levels gives rise to absorption. Reflectivity: the light reflectance of a specimen in a contact for practical applications. When the reflectivity is low, it has a high absorption coefficient. Not all light that is incident on a surface is refracted. Some are reflected. The reflectivity of a perfectly smooth solid surface at normal incidence is given by Fresnel's formula. Again, given that for most ceramics and glasses K is less than 1, it follows that reflectivity is simply related to N. For example, lead silicate glasses, also known as crystal glasses, with reflective indices of 2.6 would reflect about 20% of the incident light. This explains why crystal glass sparkles. By contrast, a typical soda-lime silicate glass with an N of about 1.5 only reflects about 4%. Interestingly though, and near resonance N will increase dramatically, and so according with reflectivity. This occurs because the various secondary waves from the atoms in the surface will cooperate to produce a reflected wavefront traveling at an angle equal to the angle of incidence. Selective reflection is thus a phenomenon of resonance and occurs strongly near those wavelengths corresponding to natural frequencies of bound charges in the substance. The substance will not transmit light of these wavelengths. Instead, it reflects strongly through absorption, where the light is converted to heat. Um, also occurs at these frequencies to a greater or lesser extent because of the large amplitudes of vibrating charges involved. If true absorption were entirely absent, however, the reflective power would be 100% on the wavelengths in question. Therefore, the reflectivity of a surface depends on its index of refraction as well. Insulators with high indices of refraction are more reflective than ones with low ends.
Hello everyone, I am Juan Carlos Sayurin and I will present the next optical properties of ceramics. The next property is translucency. Translucency is the property of a material which allows light to pass through but only partially. And for ceramics, the following factors affect the translucency of the material by either decreasing light transmission or increasing light scattering. First is the grain size. The correlation between particle size and light wavelength size is one of the most important factors affecting light scattering. In a material having similar grain size with light wavelength, the light scattering becomes very large. Materials containing particles in sizes less than about 1 micrometer or zero point 0.1 micrometer appear less opaque due to less reflection and absorption when exposed to visible light wave than those containing large particles. Materials with particles larger than about 10 micrometers have surface reflection, absorption, and refraction, while the number of particles per unit volume is small and the opacity may be reduced by reflection. The grain size also affects the number of grain boundaries. Therefore, the decrease in translucency is observed when there is an increase in the number of grain boundaries. Next is the porosity, impurities, and defects. The presence of pores in the material and the amount of these pores are more important for translucency. Pores larger than 50 nanometers result in considerable scattering, thus reducing light transmission. The impurities affect the optical features of the material and lead to changes and variations of color, which may increase the difficulty in obtaining the desired color and translucency. Next is the oxygen vacancies. Sintering conditions have a significant effect on the oxygen vacancies. When sintering is done in an environment with reduced reactions, oxygen vacancies occur. The amount of these oxygen vacancies affects light scattering as they serve as scattering centers. The last one is by refringence. It means that the refraction index is anisotropic in different crystallographic directions, as found in non-symmetrical crystal structures. Such a consequence causes the discontinuity of the refractive index at the grain boundaries if the adjacent grains do not possess the same crystallographic orientation. This situation causes both reflection and refraction at grain boundaries, resulting in diversions in the incident beam and thus reductions in light transmission. The next factor or property of ceramic materials is the fluorescence, or for both fluorescence and phosphorescence is a form of luminescence, or the ability of a molecule to absorb light radiation leading to electronic excitation. Fluorescence occurs when electrons move from their ground state to an excited state. These electrons keep the same spin as in the ground state, but when they return to the ground state, they emit energy. While phosphorescent is very similar to fluorescence, except when the electron moves into the excited state, the spin changes. Both a fluorescent and phosphorescent material emit light, but the main difference is the time in which it takes to do so. In fluorescence, the emission is basically immediate, and therefore generally only visible if the light source is continuous, while phosphorescent materials can store the absorbed light energy for some time and release the light later, resulting in an afterglow that persists after the light source has been switched off.
Hi, my name's Aliana Piamonte, and I am the next presenter for this topic, optical properties of ceramics. So just a recap, based from the previous slides, we have discussed the key properties of ceramic materials, uh, all of which can be classified as optical. So we have refraction, absorption and color, reflectivity, translucency, and fluorescence or phosphorescence. Well, optical ceramics can further be understood based on its four crucial categories, which includes transparent ceramics, single crystal, polycrystalline ceramic, and phosphor, each of which can best be explained through fabrication process, examples of materials, and other related applications. First off, what is transparent ceramics? And what do we mean when we say transparency? Well, the key requirement for a ceramic to be useful as an electro-optic material is that it should be transparent. So, pag sinabing electro-optic material, these are the type of materials na nag-exhibit ng Pockels electro-optic effect or Pockels effect. Kasi, this effect changes or produces birefringence in an optical medium induced by an electric field or modification siya ng refractive index ng isang material by the application of a direct current or low frequency electric field, much lower than the optical frequency. Examples of such materials include piezoelectric crystals and some poled ferroelectric ceramics. So, pag sinabing poled ferroelectric ceramics, this is a type of a ferroelectric material na nag-undergo ng process kung saan pinolarize siya by applying a high electric field for a short period of time. So, to create a transparent ceramic, it is necessary na bawasan or rather limitahan yung amount of sources na maaaring mag-contribute sa light scattering. Basically, optically transparent materials have the ability of transmitting or allowing light to pass through it without appreciable scattering of light. Unlike in translucent materials, they also allow light to pass through, but the photons can be scattered at either of the two interfaces or internally kung saan may change ng refraction. So, in other words, yung translucent materials kasi, they are made up of different indices of refraction. While yung sa transparent materials kasi, they are made up of components with a uniform index of refraction. Usually, yung appearance ng transparent materials, clear siya. Like, for example, lang naman, plastic cover, yung sa mga notebooks, um, yung clear na glass table, at saka yung mga um, salamin ng sasakyan na hindi tinted. Um, Isa pang example nito is magandang example ng transparent ceramic. Yung armored, yung salamin sa mga armored car. Kasi pag sinabing transparent ceramic, hindi siya yung katulad ng mga standard type of glass or resins or traditional type of glass or resins. um, Transparent ceramics have a higher thermal resistance than a glass or resin and said to be stronger and harder. So, tulad nga nung sa glass ng armored car, hindi siya, halimbawa, kapag hinammer mo siya, hindi siya basta-basta mababasag or magbe-break. Unlike kapag, kunwari, yung sa mga ordinary glass windows, kapag hinammer siya, madali siyang mag-break or mabasag. Um, kasi nga, ang mga transparent ceramics, hindi siya tulad ng mga traditional or standard na type of glass lang or type ng material na madali mag-break. While yung translucent naman, yung appearance niya, medyo malabo siya. Parang mga frosted glass style. Pero nakakapas pa rin yung light sa kanya. So, in other words, transparent ceramics are polycrystalline ceramic materials that exhibit broadband transmittance of light in the visible, mid-wave, and long-wave infrared wavelengths of the electromagnetic spectrum with transparency close or identical to standard glass. Polycrystalline transparent ceramics are useful in applications such as scintillator components, solid-state lasers, transparent armor, bulletproof glass, katulad ng example ko kanina, and nonlinear or IR optics because of its unique properties. So this type of ceramic materials are produced using high and ultra high purity powders through a tightly controlled processes like high pressure, high isostatic pressure, vacuum, and spark plasma sintering or SPS. These processes are said to yield materials with maximum transparency with higher thermal resistance, strength, hardness, and scratch resistance than traditional optical glass or resins. Yung maximum transparency niya or maintaining transparency is up to 1200 degrees Celsius and pwede madagdagan yung optical functions niya through the use of doping such as wavelength conversion. Next category is yung single crystal naman. For some applications, yung ceramic materials, they must be prepared as single crystals. But we know that most inorganic solids are polycrystalline. Kasama na dito yung ceramics. Pero may iba ding applications na single crystal siya. As for transparent materials kasi, one often uses optical glasses. But for several applications, nire-require din dito yung optical crystal materials. So, mostly kasi kapag sinabi mong optical crystal materials, monocrystalline siya. Monocrystalline materials kasi may unique properties. Like for example, here in optical crystalline materials or optical applications, single crystals are used to minimize scattering or absorption of energy. In contrast to glasses, crystals can exhibit birefringence as required for various types of polarizers, wave plates, birefringent tuners, and other optical components. Often used birefringent crystal materials are quartz, calcite, and sapphire. So, for example, yung quartz, piezoelectric material siya. And its optimum properties are usually obtained in single domain single crystals. And the difference in single crystal preparation and same composition polycrystals is that they are much more expensive since in most cases it is a much more difficult process. So transparent polycrystalline materials, they are used as alternatives or substitutes sa single crystal scintillators. For our third category, which is polycrystalline ceramics, they have a structure consisting of many grains or crystallites. The size, shape, and orientation ng grains sa polycrystalline material compared sa single crystal, hindi siya uniform kasi nga iba't ibang components ng grains ang makikita mo sa polycrystalline. So, yung strength ng polycrystalline ceramics naka-base or nakadepende siya sa size ng grain. So, as the grain size decreases, um, the strength increases. So, just like sa optical crystalline materials, ceramics and glasses also show good transparency to infrared radiation. And because of that property, it has led to the use of glasses for optical fibers for high-speed communications. And we can produce polycrystalline ceramics that are highly transparent. So in order to control the optical properties of a polycrystalline material, we need to control the microstructure and eliminate the birefringence effect during the fabrication process. Polycrystalline materials present a large number of discontinuities in their bulk due to their microstructure kasi and yung birefringence kasi leads to a discontinuity of the refractive index at the grain boundaries since hindi uniform yung crystallographic orientation ng neighboring grains. So, to prevent discontinuities in the microstructure, i-eliminate lahat ng pores and need ng controlling yung grain size. This can be achieved during sintering of the ceramic. Last category is yung phosphor. Phosphors produce light as a result of excitation by, for example, electron irradiation. Again, we're using doped ceramics for this application because doping changes the electronic band structure of the ceramic. When a material is placed in an electric field or irradiated with light, it may itself radiate light. Either electric or optical energy is absorbed, and optical energy is then radiated. A material that exhibits this phenomenon is called a phosphor, and the light radiated is called luminescence. Inorganic phosphors usually consist of a host material that could be an oxide, nitride, oxynitride, silicate, sulfide, selenide, halide, or oxyhalide, doped with small amounts of activator ions like um, rare earth and or transition metal ions. A good phosphor should absorb the excitation energy and emit light afterwards as fast and efficiently as possible. The elapsed time between excitation and emission should be short to avoid afterglow. One common application ng phosphor is through the use of fluorescent lamps. In a fluorescent lamp, the emitted light is generated by a phosphor layer which is deposited on the inner side of a glass tube. The phosphor is excited by ultraviolet light which is typically generated with a gas discharge in low pressure mercury vapor. In most cases, a fluorescent lamp produces white light rather than colored light. That is achieved with phosphors containing different emitting substances, emitting light in a different wavelength regions. The mixture is balanced such that overall one obtains white light with the desired color temperature. Phosphors generally exhibit a limited lifetime due to degradation processes, which mainly occur during operation. The degradation may simply result in a loss of luminous efficacy or also in a shift of the color appearance. So, if manonotice natin, pag sobrang tagal na ng fluorescent lamp na ginagamit natin, minsan parang dumidilim na yung ilaw. That is because phosphorus exhibits a limited lifetime. Kaya need natin palitan yung light afterwards. And that concludes my presentation.
Hello, I am Georgia Soriano. For this part, we are going to discuss the applications of transparent and translucent ceramics as new optical materials. Ceramics can perform as transparent, translucent, or opaque media depending on the light scattering, making its optical properties become important. Recall that in optics, transparent materials allow light to pass through without being scattered. The most significant factor to the transparency of ceramics is the porosity. Presence of large number of pores makes ceramics opaque. Thus, to be transparent, grains and grain boundaries should be minimized. Furthermore, crystal structure plays an important role in determining whether a ceramic can be optically transparent or not. In ceramics of optically anisotropic crystals, an additional scattering of light arises at the boundaries when the light travels from one grain to another. This is the reason why transparent ceramics generally have a cubic lattice structure. To name few examples, yttrium garnet is used for lasers. PZ and PT are lead zinc, niobate lead titanate is for electro-optics applications. The image on the top right is a transparent alumina ceramic where it can be used to create electromagnetic windows, transparent armor, and envelopes of high-pressure metal. While the bottom right image is a transparent yttria ceramic doped with different concentrations of zirconium. This ceramic can be used as an electrolyte in solid oxide fuel cells or creating more compact camera lenses. Similar to that of the common ceramics, the process of fabricating transparent ceramics as well as translucent ceramic, also consist of synthesis of precursor powder, compacting, sintering, and post-treatment. But for this discussion, only sintering techniques or creating precursor powders are included, like hot pressure sintering, where powder compact at the temperature is high enough to induce sintering and creep processes. This is achieved by simultaneous application of heat and pressure. Then there is also the hot isostatic pressing for powders. This manufacturing process used to reduce the porosity and increase the density of various ceramic materials, while vacuum sintering refers to a sintering process carried out in a vacuum equipment to achieve better results than those run at atmospheric pressure. Vacuum sintering is typically used to fabricate transparent garnet and rare earth sesquioxide ceramics. Another is spark plasma sintering. This is a newly developed method for obtaining fully dense and fine-grained transparent ceramics at low temperatures within short time durations. It is also known as field-assisted sintering or pulsed electric current sintering. Lastly, in microwave sintering, the processed ceramics themselves absorb microwave power and then convert microwave energy to heat within the samples, hence heating is very rapid. Now we turn to the translucent ceramics. Translucent materials are allowing light to pass through partially or simply transmitting most of the light but scattering it more or less. The translucency of a material can be described by translucency parameter. It is a method that allows relating visual perception to translucency. It is defined as the color difference of a material of a given thickness over white and black backgrounds. In literature, there are translucent ceramics that are made of barium titanate and strontium fluoride. But the translucency of ceramics can also be controlled by heat treatment. Looking at the images on the left, there are also other translucent ceramics and were fabricated via spark plasma sintering. Recall that in spark plasma sintering, it features a very rapid heating up process. The top image is a europium-doped perovskite with varied concentrations that can be storage phosphor for imaging plates, while the bottom image is a mica-based glass ceramic for dental applications. For comparison and looking at translucency parameter results, this one is a glass and these are glass ceramics with different mica composition. Another way to prepare translucent ceramics is making a precursor powder by cold isostatic pressing. Distortions and cracking from non-uniform particle packing are reduced in this method, convenient to yield the powder for making translucent ceramics. Cold isostatic pressing is a method of compacting powder materials into a solid homogeneous mass before machining or sintering.